Okay. First of all, I'll mention that the idea of engineering and technology and standards is not new. In 1989, the AAAS produced a book called Science for All Americans that later was broken out by grade level, called the Benchmarks, which is the document that Stephen showed earlier, that had a couple of chapters. One was about the nature of technology and showing how it's created by and improved by engineers. And the other was a chapter about the design world that we live in, our systems for transportation and building and medicine and so forth. However, it was not very prominent. It really didn't make its way into very much curriculum materials. And then in 1996, when the National Research Council developed the National Science Education Standards, which was the other set of standards that's been available for the last few years that states have used to build their standards, it was there also. But again, it was not widely used. But over the years, as it became clearer that we live in a world where we have to solve some major problems that are being caused by the vast growth of the human population on the planet. Agriculture, feeding everybody, fresh water, energy is another major problem. Science is certainly involved in all of these, but the scientist's job is simply to understand the issues, not to solve them. The engineers then use the science and the mathematics, put those ideas together to solve the problems. So, so it's gradually becoming more important, and at least a dozen states now include technology and engineering in their state standards. So, but the NGSS is taking another major leap in that direction. And so let's go on to the next slide. This is a definition of science and engineering in the National Research Council framework on which our work is based. And it very clearly states that science is the traditional natural sciences, physics, chemistry, biology, whereas engineering is a very broad term to mean any engagement in a systematic process of design to achieve solutions for particular human problems. The definition goes on to define technology as what engineers create, not just computers and cell phones, but absolutely everything from paper and pencils to toilet paper to everything that people use and create. And we actually live in a world that is really dominated by technologies, not so much by the natural world anymore. So it's important for everyone to understand that world and how it's created. So really the ideas that were planted in 1989 are really coming into fruition now in the next generation science standards. So let's go on to the next slide, which is the rationale. And one of the things that I was expecting is over the last few years, since I've been trying to infuse more engineering into science education, I should say a few decades, is I've encountered a lot of resistance by people who say, you know, engineering is not important. All we need to do is teach kids science and math, and then when they get to college, if they want to become engineers, they'll have the foundation they need to do that. Others have said, well, engineering is really just applied science. If you know the science, then it's no problem to apply it. But actually, engineering is a field in its own right, with principles and a way of thinking that's really quite different from science. It is true that engineers need to understand science and math, but they also need to apply it in a systematic way. So what I found is actually far less resistance than previously. There's been a sea change, and it's clear in so many people I talked to, including many who were very resistant before, who always felt that, you know, science was the most important. And these are the different rationales that I'm hearing. And you could think of this as the value proposition from the viewpoint of the science education community. So one is that applying a science concept in an engineering context enables science students to develop a better understanding of the science, because whenever you try to apply a concept, that's when you find out what you really understand about it, what you really don't. and you end up asking yourself much deeper questions. So the teachers who still believe that science is the most important say, I could use the engineering as a context for my kids, and they'll get the science better. Now, a different rationale is that engineering problems demonstrate how science and math come together. And this is another one of those distant goals that teachers have never seemed to be able to reach, and that's integration of science and math. And what it does, if we can achieve it, is for the math teachers to see their kids really being able to use what they're taught. And for the science teachers, being able to not only learn the science concepts, but actually apply it to problems. So engineering design brings those, and what the kids see primarily is what the goal is. So the goal might be to redesign our schools so that it uses far less energy. And right now that may be an exercise, but later on in life, it gives them a vision about what they could create if they just learn more about science and engineering as well. The third one is that solving real-world problems that meet human needs is more motivating for kids than the kinds of problems that are typically very contrived that no one really cares about. But we need to invent these problems so we can know if kids are understanding the science or the math that we're teaching them. And while I'll say the girls especially are really interested in helping people, boys feel that as well. And so engineering problems are really concrete problems. They really allow kids to put their minds to something interesting. And usually those problems involve helping people in one way or another. And then the fourth reason is that there are many, many more career opportunities for engineers and technicians than there are in science. Not to say we don't want to still encourage our students to become scientists, but this is, again, something that science teachers all up and down the K-12 or K-20 spectrum encourage your students to do, is to become scientists. But frankly, if you analyze the data from the Bureau of Labor Statistics, you find that there are, if you don't count the computer engineers, there are 4 times as many positions in engineering as there is in science. If you add in the software engineers, you find it dwarfs all the other groups. And then adding in technicians means there are at least 10 or 20 times the number of positions that students can take that involve STEM background. That's an interesting statistic that NASA, who we always think of as employing primarily scientists, employs 9 engineers for every scientist. Because NASA, after all, has to get those rockets up into space and into orbit. So that's really the value proposition, that wherever you fall in the rationale for it, engineering design is a really good thing to integrate into the sciences. Now the next 4 slides I'm going to breeze through just so we have time for discussion. But Stephen outlined that these science and engineering practices are redefined and updated, realizing that scientists and engineers don't just spend all their time doing experiments. They ask questions, use models and simulation, analyze data. They spend a lot of time arguing, creating arguments based on evidence, and in many cases changing their minds about things. Scientists do these things to better understand the world. Engineers do them to solve a problem and meet a practical purpose. The purpose of these 4 slides is to show among the 8 practices how each of them, how there are similarities and differences between scientists and engineers, or the practice of science and engineering. They're very similar in many ways. In other ways, they are different. And the way I think about it is that my rule of thumb is, if the work you're doing is to achieve a goal, then you're doing engineering. If the work you're doing is to answer a question, then it's science. And so let's skip these, and I'm going to end with my last slide, slide 18, which is at the top. It says, performance expectations combine practices with core ideas. Did you find the slide, Angie?
Yep, there. Yep, we're on it right now.
Okay, good. Now, I picked a life science example because a lot of people think of engineering as being physical science. They don't really think of it as chemistry, like chemical engineering, or life sciences, genetic engineering, and so forth. So these are two performance expectations, what we expect students to be able to do to show they understand a science concept. From a science perspective, evaluate data to explain resource availability and other environmental factors that affect carrying capacity of ecosystems. So carrying capacity is a concept, scientific concept, that allow for the analysis of ecosystem. How many of each population can be carried by the ecosystem depending on the resources, both biologic and abiotic resources. So here's another performance expectation in the area of ecology that has an engineering perspective, and that's design solutions for creating or maintaining the sustainability of local ecosystems. So to be able to do that, the students really need to understand what ecosystems require to be sustainable over time, and that is to develop stable populations of organisms.